All right, so last class we had just talked about the change of base formula, right? Am I remembering this right, or am I in my other class? Change of base formula, right? Yeah.
Yes.
So we had a couple examples that we were looking at. We had just looked at these three examples. And I had said that you can't pass a negative through any logarithm, no matter what the base is. So C here was going to be undefined, right? But log base 3 of 6, this could be rewritten as the ln of 6 divided by the ln of 3. And log base 2 of 3 can be rewritten as the ln of 6, or I mistake, the ln of 3 divided by the ln of 2. And this is, of course, because of the change of base formula, right? Change of base formula says that log base b of x is equal to the ln of x over the ln of b. Now for a second, we're going to use this to answer another question. What's this? How are we going to find the derivative of log base b of x? Well, we're going to start by rewriting log base b of x using the change of base formula. Well, the ln of b, this is just going to be a constant, so we can pull that out. So what we're going to get, what we're left with, is 1 over the ln of b times the derivative of the ln of x. Well, the ln of x, that's just 1 over x. So what we're going to get is 1 over the ln of b times 1 over x is equal to the derivative of log base b of x. Really quickly comparing that to what we've got here. Log base a of x, the derivative, is equal to log base a, same thing. And just to show that that first property for a to the x is correct, let's write that one out too. P dx of a to the x. Well, this thing can be rewritten as d dx of e to the ln of a x, right? of all of this, you can think of this ln of a times x as its own little function, right? And we know that if that's the case, then d dx of e to the u of x is equal to e to the u of x times the derivative of u of x so we get e to the ln of a x all times the ln of a, which we can rewrite as the ln of a times a to the x. Make sense? Everybody cool with this? So of course we can generalize these to log base a of some function of x, or a raised to some function of x, and we get the general properties as well, right? So having said that, more radioactive examples. Here we've got the half-life of, I think it's radium, right? No, this is not radium. This is something else. Carbon isotopes. So the half-life of a carbon isotope is 5,715 years. We're given a gram of it. Excuse me. We're given a gram of it and told that the amount with respect to time can be modeled as 1/2 raised to the t over 5715. And then asked to find what the rate of change is when t is equal to 10,000. So what we're going to have to do then is apply the derivative. So we've got a as a function of time is equal to 1/2 raised to the t over 5715. Taking the derivative. This is going to come out to be the derivative of a raised to some generalized function, right? So we're going to have the ln of 1/2 times 1/2 raised to t over 5715. And the derivative of this exponent, right? Which is just going to be 1 over 5715. Everybody cool with this? All I've done here is applied the second rule directly onto it, right? Yeah. From here, all we've got to do is plug in 10,000 and we get the answer. So comparing what we've got on the board to what the book has to say about this problem. When they calculate the derivative of the amount with respect to time, they get out the ln of 1/2 times 1/2 raised to that exponent, all times the derivative of that exponent. Same exact thing, right? Then they plug in 10,000 and they went ahead and calculated it. So having said that, we have what's called the law of exponential growth and decay. But before we get there, just some notes about this idea of what it means to be exponential yet again. Whenever something grows or decays exponentially, all we're saying is that the rate of change is going to be proportional to y. So we're saying the rate at which it changes is proportional to its current state. That's it. Now, having said that, you got to figure out what y is. Guessing what y is, we guess that it's equal to c times e raised to the kt, and then plug it into this differential equation that they've given us. We can prove that it satisfies these conditions, right? That's all they're trying to say here. Having said that, I would like to actually show you how this is proved. And I'm going to do that on the board. And then flip to the next slide. So we're told that something's going to grow or decay exponentially. So what that tells us is that the change in our y is going to be proportional to our y. But notice if this is the case, we can rearrange this thing as dy over y is equal to k dt. Now we're going to use something from the next chapter. I just want to introduce the idea of it here. It's going to be called the integral. What this sign means, for all intents and purposes, is we're going to undo the derivative with respect to y here. So we can think about this in reverse. If the derivative of a thing with respect to y is equal to 1 over y, what was the thing? In other words, this is telling us that the derivative of our function here is going to be equal to 1 over y. That's what this sign means. Like I said, we'll explain more of it come next chapter. But given that, that means this thing is going to be equal to the ln of y. Make sense? And this thing over here is just going to be equal to kt plus c. And that makes sense, right? Because if we take the derivative of this with respect to t, we're just going to get k, right? And if we take the derivative of this with respect to y, we're just going to get 1 over y. Yep? Everybody cool with this? So now, combine, if we raise both sides, or if we take e and raise it by both sides of this, we get that e to ln of y is equal to e to the kt plus c. At this point, I'm going to say, let's call this C1, call this C2, or my mistake, still C1. And I'll show you where C2 comes in just a second. Well, this thing's just going to be y, right? This thing is going to stay e to the kt, but now we're going to have the ability to pull out this EC1, right? Well, this is still a constant, so why don't we call it C2? Lo and behold, we get our solution, right? What we just guessed it was, we just proved over here. The only reason they use this guess and check method is because we hadn't introduced the antiderivative yet, or the integral. But I figured it's a good time to go ahead and kind of ease us into this idea. What this thing, we're going to find in the next chapter, does is undoes the derivative. So really quickly comparing, same exact idea. Go ahead and actually type it out for everyone. So what we have here now is the law of exponential growth and decay. Let me turn off Outlook really quick. Okay. The law of exponential growth and decay is just telling us that things that grow and decay exponentially are going to behave according to a particular model. I should have 2 of these. And we have the other case. It's going to look something like this. This is C here. This is going to be the case y is equal to C e to the t. B is greater than 0. So all this is saying, all this law of exponential growth and decay is saying that if something grows or decays exponentially, it can be rewritten in this way. And we can see how everything is going to change according to B this way, right? We can see that if B is less than 0, then this thing's going to decay. B is greater than 0, this thing is going to grow. So having said that, a common application of this is to problems involving half-lives. So for that reason, here's a bunch of half-lives that you might want to refer back to for homework. This is in slide, what slide is this? Slide 73. Slide 73 in week 9 under exam 3 on Blackboard. All right, so let's use this idea of the law of exponential decay. So in this problem, we're given that we have 1 gram of radium to start off with, right? So at time equal to 0, we have 1. Now, what we want to find is if we're going to have more than a half gram after 1,000 years. That means we're going to have to go back to that table. But let me actually jump ahead because this will be a little bit more clear jumping ahead. So this initial quantity is telling us that C e to the k 0 is equal to 1. Well, if that's the case, then e to the k times 0 is just going to come out to be 1. So C must be equal to 1, right? Make sense what I mean? So now we know just from this that A as a function of t must be e to the kt. Now going to our list of half-lives here, we're working with carbon, right? Radium, my mistake. So because we're working with radium, we know that at 1,599, a half. And this is equal to e to the k 1,599. And we can solve for k from here, right? Taking the ln of both sides. Now solve for k. And get back the rest of our model. Still comparing really quick. We're told the half-life is 1,599 years. So y is going to be equal to 1/2 when t is equal to 1,599. We've used that to form part of our problem that we can solve for k now, right? We solve for k. We find that k is equal to the ln of 1/2 over 1599. Cool with everyone? Having said that, just some basics of how to go about solving these problems. You're going to want to write two sets of conditions that relate y with time. So let me kind of fetch this out a little bit. We're assuming that we have a model that looks something like this. And then we're going to assume that we know something about our model at time 1. What do we want to call this? Something 1, something 0. And we know something about our model a little bit later. Using our assumed model and our two conditions, we're going to solve back what the constants of our model will look like or will be. Cool with that? Yep. Dope. So having said that, I am going to let y'all work on this example for a couple minutes. This is page 77 in the notes. I'm going to give y'all like 5 minutes to try to get this problem done. While y'all are working on that, I'm going to step out for just a second.
Hello, Christian.
So have we figured it out yet? This problem takes some playing with, I will admit that. It takes some thinking about. We're told at time equal to 2, we have 100 flies. And at time equal to 4, we have 300 flies. So what are we going to do with this? Well, let's really quickly just write out both of these just to see what we see. All right, so A at time equal to 2, this thing's going to be C e raised to the k times 2 is equal to 100. And at time equal to 4, it's going to be C e k times 4 is equal to 300. Is there anything nice we can do with this? Well, if we divide the two of them, we can cancel out those C's, right? So why don't we do that? Why don't we say A at 4 and A at 2, divide these, right? This is going to come out to be e to the k times 4 divided by e to the k at 2 This is all equal to 300 divided by 100, or just 3. Well, hey, we can rewrite this, can't we? We could rewrite this fraction as e to the k times 4 times e to the negative k times 2. Well, these share the same base, so we can pull the exponents together, right? And get e to the k times 4 minus k times 2. Well, that's convenient because now we can factor out a k, right? So when we factor out this k, this is all going to become e to the k, 4 minus 2, or just 2, right? So instead of writing another line below, I just went ahead and wrote it at the top here. That's nice, because now we can apply the ln to both sides, right? This tells us that the ln of 3 is equal to 2 times k. Excuse me. divide both sides by 2, and we solve for k. All right, so now we know k is equal to the ln of 3 over 2. So looking at these two cases now, let's substitute in what we know k to be, the ln of 3 over 2, this is times 4, this is the ln of 3 over 2 times 2. Well, hey, check it out. In this case, the 2's cancel. That's convenient, right? And in this case, they don't totally cancel. We get 2 times the ln of 3, right? So why don't we use this first case? It's a little bit easier to work with, right? So A at time equal to 2 is equal to C times the E of ln of 3 is equal to 100. Now we can just solve for C. This tells us then that C is equal to 100 divided by the ln of 3, E times the ln of 3, or E raised to the ln of 3 is just 3, right? So we can divide by 3. So now we have what C is as well. Now that we have all of this, put it all together and solve for what our model will say about the number of flies at day equal 5. So jumping to the next slide, comparing all of this, we have our 2 initial points. We set them up so that we can solve for k. Once we solve for k, we solve for c. And after we solve for c, we put it all back together and find out what our model tells us about time equal to 5. Having said that, since there is only 5 minutes left, yeah, we can get through the rest of these. In this other example, we've actually already done almost this exact same problem. The difference here is we're given a little bit more information. We're asked to find what R has to be, given that the amount and an account doubles after 6 years. So what we're saying is we have this case here. Let me erase all of this. We're talking about an account which is compounded continuously. So we know that P is equal to, my mistake, A is equal to P times E raised to the RT, right? We're told, let me write this as a function. We're told that at time equal to 6, this thing, PTR 6, this thing's going to be equal to 2 times the amount we initially put in. So 2 times P. And that's it. That's all we're given. What we want to do now is find R. What R would make this happen? To find that, we're going to say, all right, we know that P times E to the R times 6 is equal to 2P. Well, that means E to the R times 6 is equal to 2, right? Taking the ln of both sides, we get R times 6 is equal to the ln of 2, or R is equal to the ln of 2 over 6. And that's it. That's all there is to this problem. We just wanted to know what the annual rate of interest was. What time is it? Don't quite have enough time to go over this problem entirely, so I'm just going to jump to the next slide and really touch on it. I'm going to really quickly touch on it. So what this problem is going to tell us is that at time equal to 0, we're going to have 100,000 units of a thing, and that this thing can be modeled as exponential decay. Using that and the fact that at time equal to 4, we have 80,000 units, we can set up the rest of our system and solve for C and K. Make sense? So just because at time equal to 0, Y is equal to 100,000, we automatically know that C has to be 100,000. It's a gimme. Now we have to solve for K. So setting up our system, we have Y is equal to 100,000 times E raised to the KT. We'll have T equal to 4. Y is equal to 80,000. Divide both sides by 100,000. We get 0.8 is equal to E raised to the 4K. E to the 4K is equal to 0.08 or to 0.8. We can take that ln of both sides and then divide both sides by 4 to solve for K. Now that we have our model and all the constants, we can actually test values, right? You go through and say, all right, how about after 8 days? How about after 9, 10, or months? I mean, 9, 10, so forth and so on. Having said that, I'll let y'all go. I'll stick around if y'all have any questions.